All right. Hello, everyone. Welcome to today's Corundum developer meeting. Not a whole lot on the agenda for today, mainly just some status updates over all the stuff that I've been working on recently and, some stuff that's potentially needs to be done. So, all right, let's go ahead and get into it here. So, first off, there's a couple of minor bugs that I'm working on and a couple that have been fixed. I'm going to talk a little bit about the DRAM integration that's now in the main repo and a couple things that I'm hoping to do in relation to that going forward. The clock information register block, I finally got that knocked out off the to-do list. That's implemented and I think it's in the main repository. If not, it'll be there soon. So I'll talk about that a little bit and then everything else is kind of carryover stuff. So the batch completion right support, I'm still working on that, but that's been backburnered for getting some of this other stuff out of the way. And then everything else is kind of carryover to do items. All right. So let's see. Bugs. So we have the parent PCI Express hard IP bug in relation to stuff getting dropped under heavy load. Still need to make some modifications to the DMA engine for that, but I've been sidetracked working on a couple of other things. I have not been able to trigger this bug with the, you know, default design in the repo right now. It only seems to get triggered when it has the newer completion write back support enabled, presumably because that changes something about the performance characteristics. So not a super high priority to get that fixed unless I can um, trigger that with the default setup. So anyway, I'll get that fixed hopefully soon, and that'll be good. All right. Next,
Alex,
yeah, sure.
is this TX or is this RX? The drop
Um,
of operation, or is this both?
it was only happening if I exerted both TX and RX at the same time
Okay.
pretty hard. If it
So
was
what
just
what
TX or just RX, it wasn't happening. If you hit it both at the same time hard enough, then it'll
so what
trigger it.
we saw is that at certain load on the Intel side, we see that the DMA engine at some time responds to a descriptor fetch request with empty, and then this DMA operation is dropped as well. So basically the packet is lost.
Okay, well, this doesn't cause lost packet. This causes the entire data path to hang.
Oh, okay. Yeah, that's a different
So
thing.
that's a different
Okay.
thing. Yeah. This is a much more serious problem. Yeah. Um, right. But I'm hoping to get this fixed relatively soon. And this only seems to be a problem when you're running at like full 100 gig line rate on with the newer completion write back support enabled. I guess because that just produces a lot more write traffic or something along those lines. I'm not 100% sure, but yeah, it's an issue. That'll get fixed soon. So yeah, okay. So the next thing is the PCI Express 4K read request bug. Had a couple of issues with respect to issuing kind of maximum size read requests. This one cropped up again with the new shims. Um, Small mistake in terms of regenerating the kind of MSB bit in the TLP size field. Um, so I have that fixed now, so we can generate, 4 4 KB read requests, and the packet will actually be issued correctly over the PCI Express link. So that one was only affecting Xilinx devices, but that has now been fixed in the upstream repository. And then another issue that I think this has been an issue for a while, but I just kind of dug into it a little bit deeper. There's a problem with the AXI Stream FIFO in terms of how it's using the memory primitives basically, and well, more in terms of how Vivado is interpreting things. So I'm not quite sure on the Intel side if it makes much difference, but basically Vivado is not recognizing the pipeline registers properly that the FIFO is inserting after the memory, and as a result, the registers don't get pulled into the RAMs, and this reduces the timing performance because it doesn't have the pipeline registers, and it prevents URAM inference for large RAMs. So more than 4,000 entries deep. It should infer like a URAM array sort of thing. It doesn't because it's like, oops, I don't have enough pipeline registers, so I can't do that. So what I'm going to work on over the next few days, hopefully, is a reworking of the FIFO modules to make them look more like the memory template, basically from Xilinx. I think the problem in this case is not necessarily the pipeline registers themselves, but it could be some of the other signals effectively. There's something about how the FIFO module accesses the RAM is preventing Vivado from properly detecting it as a memory. So anyway, I have some ideas on what to do about that. So I just got to test a few things and see if I can make that work properly. That's going to be important if you want to have like a large RX FIFO or something like that and properly use URAM. If it's using the wrong primitives, then that's a problem. And also for timing reasons, you need those flip flops, to get pulled into the RAMs properly. So that's something I'm going to be working on. All right, and then the clock info register block. This has been on the to-do list for quite some time. Finally went ahead and got it knocked out. The idea is pretty simple. It exposes a couple of pieces of information about the clock frequency configuration, the clocking configuration. So right now, the block, it exposes kind of two parameters indicating the frequencies of a couple of clocks, and then a bunch of frequency counters. So it exposes the frequency of the core clock, just kind of as a period in nanoseconds, and then it also exposes the ratio or the frequency of the reference clock, again as a period in nanoseconds, and then it measures the frequencies of all of the TX and RX clocks, as well as the core clock with respect to the reference clock, and exposes all of those in hertz, basically. So you can just read all those out, and that can be used for debugging. And then also, if you need to know what the precise core clock frequency is, it gives you that, which it can be useful in terms of things like rate limiting. If you need to do something in the scheduler with a particular number of cycles or something, that you can determine what that frequency is very precisely. And the reason that's kind of important is the core clock frequency is not necessarily very accurate because that's coming from the host. So who knows what oscillator that's generated with? It might have like spread spectrum or something applied. I notice on a lot of cards when you do the time sync with PH8 assist and it's doing the sync over PCIe, that there can be a pretty large frequency offset on that internal oscillator, or on the PCI Express, core clock. So not exactly sure all the reasons for that, but that is a thing to be aware of. That frequency is not necessarily going to be accurate. So with this register block, it takes all the measurements using the much higher stability Ethernet reference clock that's used to drive the PTP clock and whatnot. So yeah, that's that. And hopefully that's going to be useful for diagnostics. And I think the people at Emily were asking about having some of that information available. So it's now in there, and I believe that's in the upstream repository. If it isn't, then it will be soon. Yeah, so that's done. Okay, and then moving on to the DRAM integration. All right, so I talked about this last time around. The idea here is to provide a connection between the application section and any on-card DRAM or HBM. So depending on the part and depending on the board, you might have different amounts of HBM and DRAM available. So there's several components to the DRAM integration. One of them is just providing the AXI stream pass through from the memory controllers at the top level all the way down into the application section. But eventually, what we want to do is provide some infrastructure as well inside of Corundum that can be used to connect the memory controllers to a PCI Express bar that can be used for host software access and PTP DMA, as well as a connection to the DMA subsystem, such that you can mix and match buffers that live in host memory and buffers that live in on-card memory, and it'll do the right thing transparently without having to jump through any additional hoops. Another thing that I was thinking about is potentially providing a couple of different selectable clocking modes for this. So the way it's set up right now is basically what I call fully asynchronous, where every port is potentially driven by a separate clock, and all of these clocks will be provided directly from the interface clocks, and this gives you kind of the minimum latency, right? Because there's no additional CDC logic or anything like that. It's just coming straight from the MIGs or the HBM controller or whatever. And if we add any additional internal logic in terms of connecting this up to the PCI Express bar space, we'll do that with a small kind of AXI switch component that will run in the same clock domain as the MIG. So we won't add any CDC logic between the application section and the memory controllers. But this is not necessarily appropriate for every application. In some cases, you're not going to want to add a bunch of your own CDC logic. It makes sense to put all of these interfaces in the same clock domain. So the second mode would be synchronous, where async FIFOs are inserted internally to sync everything to some internal clock. So I'm thinking there probably even needs to be a selection here. One option could be we're going to take the first MIG clock and synchronize everything to that. So it's not the same as a core clock, but if you have like 2 or 4 memory channels, they're all running at the same clock rate. You don't need to worry about crossing all those. You can just connect a AXI crossbar or whatever. Another option is to cross it to the core clock, so everything's just running at whatever the PCI Express clock is. Piece of cake. Flip side, throughput in that case might be reduced because of the if that clock speed is lower than the big clock, that could potentially be a bottleneck, or maybe not. Depends on the traffic patterns and whatnot. And then the third option is to have like an additional custom clock, and then you synchronize everything to that. That's another thing I've been thinking about is, if the application section wants to run at, say, a higher frequency than the core clock, it might make sense to provide some pass-through capability for additional custom clocks. If you want to drop down some PLLs or something like that at the top level, generate some new clock frequencies, having a way to pass that through in a standard way would be a potentially useful feature. So if we add something like that, then we can also use that for clocking the memory interfaces, and we can kind of roll all that into the same kind of feature. Anyway, so there's potentially some stuff there to discuss if people have some ideas. Right. So the to-do for this is basically all of the Intel devices. I don't yet have the DDR and HBM controllers set up. Haven't done anything with 7 series. Basically just UltraScale Plus. Pretty much all the boards have all of the MIGs and HBM controllers active for UltraScale Plus. And then I also need to do all of the kind of higher level integration in terms of setting up the PCIe bar and the DMA subsystem. So a little bit more details on what that interface is going to look like. So currently, the design provides AXI light ports for kind of the NIC control and for the application section control, and those are exposed on PCIe designs as bar 0 and bar 2. So what I want to do is add an AXI port that will be exposed as bar 4 to access on-card RAM and potentially a few other things. So the idea here is to support full AXI bursting and interleaving, so you can get very high performance. This is opposed to AXI Lite, which doesn't support any kind of interleaving or reordering. and there's no burst, and the maximum transfer size is 32 bits. So with the full AXI interface, you can potentially get much higher throughput, and this can support being a target for peer-to-peer DMA, as well as write combining from host software. And this can also be connected to the application section as well for low latency operations. So if you want to write, a big block of data straight to the FPGA, that's potentially a useful capability if you're doing latency critical stuff. Having a way to pass that straight through is potentially useful. And my thought here is to internally share this port with the DMA subsystem. So as a result, when a DMA operation is issued, it can be sent to either the host-facing DMA interface over PCI Express or this internal AXI port based on the address. So for operation in PCI Express, what you would do is look at the configured addressing for bar 4. And if the requested address falls into that range, then you would hand it off to the AXI DMA engine versus the PCIe DMA engine. And potentially you can do something similar for a design targeting, an SoC style part. We'd also have to add some parameters, I guess, for passing along the address-based configuration such that this stuff can be routed correctly. So those are kind of my thoughts at this point for what I think this stuff is going to look like going forward. If anybody has any questions or comments, we can certainly discuss that. All right, so moving on to batch completion write. Like I said, this one has been backburned a little bit. I need to fix the PCI Express bug, and then I've been sidetracked. The research project is starting to ramp up again, so I've been working on some stuff related to that. But I'm going to circle back to this once I get that that PCIe bug squared away and start getting this upstreamed at some point relatively soon, because this will definitely have some effects on performance to speed things up. All right, let's see, what else do we have? I guess I still have all the slides from this in terms of all the graphs, but there's nothing new for any of this. So if anyone has any questions or comments, go ahead and fire away. I can certainly pull this stuff up and we can go into it in more detail. Let's see. So after that, we also have the variable length descriptor support. Again, talked about that before. I'm not going to spend any more time about that today because there's nothing new. And then we also have the 10D, 25D switching and the management software, which, again, those are still kind of carryover until a few other things get implemented. All right, and then the to-do list for the stable release. I guess I don't have anything on here for the RAM integration, but that's now implemented as well. So yeah, I guess that brings me to the end of the status update. So at this point, we can open the floor to any sort of questions and comments that people might have. And then if nobody has any questions or comments, then MLE can take it away, as usual. Anybody have any questions or comments? Or any points they want to discuss? I know there was some discussion about the some of the RAM integration stuff. I guess it was Leon that was had some ideas about that potentially, but I guess he's not on here at the moment. All right. Well, if nobody has any questions or comments, then I guess Ulrich and Joachim, you guys can take it away.
I guess Joachim actually made it to the meeting, so I will let him step in.
Yeah, I see him on the list, assuming he can figure out his multiple mute buttons.
Yeah, that was the last mute button.
Okay, cool.
Yeah,
We can hear you.
sorry.
That's
Yeah,
important.
sorry. I joined late today.
No worries, no worries.
So yeah, actually, yeah, we do have questions, or perhaps to put in other words, perhaps we could continue the discussion around our
Right.
yeah, problem which causes our TCP traffic to
Well, just real
be
quick before
reduced.
that, I guess since you joined late, I don't know if you saw, but I got the clock info register block stuff in the upstream repository now, so that will give you information about the core clock frequency and a few other things. So I know you guys were asking about that a while ago.
Yeah,
Finally
great.
got around to
Okay.
knocking that out. So,
Mhm.
and it's just one module and one TCL script. So if you guys need to backport that, shouldn't be a big deal.
Okay, very nice. We'll have a look at that.
Yeah, I haven't implemented a whole lot on the software side, but I did add a couple of hooks, I think in the library for reading stuff out. So if you run like the dump tool, it'll detect that that block is there and, you know, read everything out and print out the frequency measurements and whatnot. But yeah, we should add probably the equivalent calls on the driver so you can use them from the extension module and whatnot. But that's a pretty simple thing to do. So
Okay, sounds good.
anyway,
yeah, so perhaps a little bit of an update. I don't know how far we were last time, but I'll just start. In the meantime, I'd say we determined that the TX checksums of TCP packets seem to be the problem in general. In detail, it looks like that of a certain amount of packets, the TCP checksums are just incorrect. And roughly the amount of packets where via capturing we see that the TCP checksums are incorrect, roughly is equal or is in the range of the reported retries by IPERF, which do happen.
interesting. Are you familiar with a tool called NSTAT?
NSTAT, no, not yet.
Okay. It dumps out a bunch of network stack related counters.
Yeah, most likely it dumps netstat then. We have been looking
possibly,
at that.
yeah. So
Yeah.
it dumps out things like you know, counters related to IP, TCP, UDP, that sort of thing. So it will have some counters in there, I think, that'll be related to TCP packet drops. So if you know, if the receiver is getting packets with bad checksums, bad TCP checksums, and there's probably going to be a counter in there somewhere that would increment. And the cool thing about NSTAT is, I think by default it does basically like a dump and zero sort of operation. So the idea is you run NSTAT, you ignore what it prints, then you run your test, you run NSTAT again, and it prints out only the counters that have incremented since the last time you ran it. So
very nice.
Super simple.
Yeah, we actually did another trick, or found out. We usually use the same machine as the source and the sink in our bridging scenario. So just to remember, our test cases have a source PC with a standard NIC, which also acts as a sink, and in between via switch magic, we have our custom card with our MQNIC design, which does bridging, layer 2 bridging between two ports of the card. And for this setup, we are using the sink and the source and have them on the same machine. So we have to use namespaces, and a nice effect is that if you create a namespace, these counters under proc netstat are also reset to 0. So a new namespace gets its counters reset to 0.
And also each namespace has its own counters too, which is
yeah,
definitely useful.
and that, yeah.
I think nstat is also aware of all that too. So yeah, probably because it's looking at the same counters. So yeah,
most likely, yeah. Okay. Yeah, so we also looked at these counters, and they basically match. They report in the same range. The number is in the same range. It's not exactly the same. Perhaps that's the point.
Well, is it higher or lower? I mean, I guess you could be seeing a couple of different sources of packet drops. So if the number of checksum errors is slightly lower, then that would be reasonable. If it was higher, then it'd be a head scratcher.
Yeah. I think it was lower, the reported number. Yeah.
Okay. Well, so that definitely points to some sort of a problem in the checksum computation code.
Yeah, and
interesting that it only affects Intel devices. So
yeah.
So that points to it could be some sort of a a synthesis issue, maybe something about that code.
Yeah.
The Quartus tool doesn't like.
Yeah, we also thought about that. We kind of roughly checked the code and thought about it, but up until now, yeah, we did not see anything obvious, or I have to say, our colleague did not see anything obvious. We didn't expect anything obvious though. So what we've now done is perhaps to add that. Uli, do you want to add something?
Yeah,
to that?
I want to add something because you haven't been with us end of last week. So yeah. I did some analysis of the captured right side traffic where the bad packets are in, and I came to the conclusion that all the packets that have incorrect TCP checksums had, so from a computation perspective, I would say that originally there was the correct checksum in this packet, and then the checksum engine calculated another checksum, including this correct checksum, and inserted the bad checksum.
Oh, okay.
So it really seems that packets that shouldn't have been recalculated by the hardware got updated with a then incorrect checksum. Because I think usually this checksum field is 0, right? So it's not important if you include or exclude it during checksum computation. But if there is something in there, then it kind of derails this.
Oh, so okay, so the way the checksum computation works on the transmit direction is that the IP stack computes the partial header checksum and inserts that into the field. So that checksum field will actually have the wrong value because it doesn't include the payload. And then the hardware, it basically just computes the checksum of the payload and then updates the field in the header. So it reads out the value, basically adds it to that and writes it back.
Yeah, so what I did is I just worked on the captured data. So what I by accident did, I recalculated the overall checksum of the TCP portion of this packet. And just before I had ScapeI update this TCP checksum field so that the correct one was in there. And then I manually calculated with the ScapeI util function another checksum about across all the TCP portion, so header and payload. And then the result was the checksum we saw being there added by the hardware. So that was the originally captured checksum.
So,
and that was present for the, I don't know, 200 something packets I checked out. So there is some systematic here in there. So it might be not exactly the one that I described, but it's definitely some systematic thing here.
Okay, so it seems like what the stack is computing the checksum of the whole packet, and then for some reason the NIC is doing its checksum offload, even though the checksum has already been computed by the stack. That's
the idea, right? So that might be the case.
Yeah, Uli, perhaps at this point we have to add the following piece of information. In the meantime, we also added various counters to the checksum TX checksum module itself, counting the number of requests it gets via its control interface, counting the number of times it gets it with enable, meaning please do calculate the checksum and insert it, and counting the number of times it gets that request with enable equals 0, meaning do not calculate. And then also another counter which counts the number of times that checksum actually got inserted or overwritten in the data stream, just to make sure. So the first result was the number of requests, enable or disable, meaning the sum of it is always the same as the times it got inserted. So no worries there. That seems to be correct. But we then also added on the software side a simple counter which counts the number of times the Linux network stack wants us or orders the hardware to do the TX checksum calculation. And that's where we see a difference. In this case, it's a difference that the software number of requesting the hardware to do the TX checksumming is lower than the hardware counter of the counter where we count the control interface enable equals 1. So it seems like the hardware is doing extra calculations, more calculations than the software wants it to do. And another data point is, and that's good, that did I already mention that enable plus disable sum is also equal to the number of packets the software thinks it has sent. So that's also good. No worries there. So the only odd thing is that the hardware does more checksum calculations than requested by the software.
So basically, that enable bit is getting set in a few cases where it shouldn't.
Yeah,
sounds like.
Right. Yeah.
Interesting.
And the difference between these numbers is again roughly in the same range as those retries reported by iPerf. So now the question is are all these extra calculations, are all these the wrong ones we see? I think we don't know that yet.
Well, I mean, don't know that yet, but that's a good assumption. If it's generating the checksum on a packet where it's not supposed to, then the result is going to be the wrong checksum in that packet. So, yeah, those are probably linked. So one thing to keep in mind here is we can actually turn off the checksum offloading for both TX and RX separately using ETH_tool. So that would be a simple test. Just turn off the offloading and see what happens. Because if that works, then that would rule that out as a problem.
Yeah, the problem there is then that without having TX checksumming enabled, the CPU experiences another load request So the load for the CPU is higher. It has to calculate the
Well, right, yeah,
checksums.
obviously the CPU load is going to be higher, but it's a question of whether you're still seeing the same performance issue. Or I
Yeah,
guess maybe you do.
yeah,
Okay.
yeah. But unfortunately, and we also saw that in other scenarios where the CPU load is higher, for example, when capturing on the bridging machine, which bridges the two ports of our card, when we do capturing there, then the CPU obviously has more to do. And then the effect is hidden, I would say. And paradoxically, the bandwidth then is also a little bit higher, meaning not as low as those 3 gigabits per second. So it seems like the higher the CPU load, and yeah, kind of the less back-to-back PCIe Express load there is towards or from the NIC, the MQ-NIC card. It seems that the less that is, the more stable the situation gets, meaning less retries and a more stable or yeah, a stable bandwidth from 1 second to the another, not so much jitter involved as before. So that's another complication where we think that the effect can be hidden by more CPU load, to put it simply.
Well, here's
and
what I'm
that's
trying to
also
figure
the
out.
case
So
for.
here's what doesn't make sense at the moment is that you said you're doing bridging at the Ethernet level. So if you're doing bridging at the Ethernet level, why is the card computing and inserting any checksums whatsoever?
Yeah, very good question. We also asked it ourselves and were totally puzzled. There's a great software technique called GRO, generic receive offload. And that's not only a hardware feature, it turns out it is code enabled in the lower layers of the Linux network stack, which is active also for any NIC, which carries out some
so
software
GRO is
offloading.
combining the packets on receive. I
Right,
see.
yeah. And so since it combines it, it has to recalculate the TCP checksum, replace or adjust the headers. And on the outgoing bridge interface, well, it has to revert that. And that's
that's
the
why
reason.
it's doing okay.
Right.
Okay, and then that would explain why it's only TCP packets that are affected, because those are the only ones they combined in GRO. So it doesn't need to touch those in the other direction, or so it needs to touch those in the other direction.
Disabling.
Have you tried? You've tried disabling GRO. Sounds like okay.
Yeah, disabling GRO again puts more load onto the CPU, and so it seems that the effect is hidden again.
Well, the effect in terms of the checksums are no longer wrong, or
yeah, that's what I call the effect: checksums being wrong, and therefore retries being high or higher than expected, and bandwidth being simply
right. Well, I mean, it seems like if you turn off GRO, then the CPU load might be higher, but it's not requesting any transmit checksums, right? So, so that kind of indicates that this is probably the root cause of the problem here, right? Because if you were getting these checksum issues even under that circumstance, then you would still be seeing those retries, right? So yeah, it's definitely kind of ruling out other possibilities, right?
I mean, what I currently still don't understand about GRO is why exactly the CPU has more to do in the case of pure layer 2 bridging. if GRO is disabled. That's kind of what I.
Well, does the bandwidth change very much? Right, and if the bandwidth is higher, then that would explain why the CPU usage is higher.
Yeah, the bandwidth is actually higher. I mean, if before when the effect hits, the bandwidth is around 3 gigabit per second, sometimes a little bit more, sometimes really a little bit less, but very jittery. When looking at a 30-second run, every second look has a different bandwidth, and as soon as the CPU load gets higher, the bandwidth is first of all stable. It's a kind of a stable report from second to second, always roughly the same number, and in most cases it is higher. So having a little bit of more load, like disabling GRO, makes a little bit of more load, and then we get a bandwidth around, I guess it was around 7 gigabit per second. If we do additional capturing, the CPU load gets even higher, but then the bandwidth is still stable, but moves to around 5 gigabit per second. So the effect of the CPU load seems to be, I don't know how to say that, twofold. Adding a little bit of CPU load makes the effect go away.
Right. So my point is, I think that first point is a bit of a red herring, right? It seems like if you disable GRO, then you're not getting any of these bad checksums in the first place, right? And that doesn't really have anything to do with the CPU load necessarily. That's kind of an effect, right? If you disable GRO, then you're not getting any checksum errors, so you're not getting any dropped packets, so the bandwidth can ramp up higher, and that results in more CPU load.
Yeah.
Right?
Yeah.
So I think that's what's going on here, right? If you turn off GRO, it the issue in terms of the checksums seems to be going away, and then the CPU load and the bandwidth ramp up higher.
Yeah.
Well, more like the bandwidth ramps up and then the CPU load follows. So
yeah, but at a certain point, ramping up the CPU load even more by, for example, running
right. If you're
extra
capturing, there's more stuff going on. So it's also possible. Okay, so it's also possible that when you capture it, it may turn off GRO or change how GRO works.
Okay.
Right.
Yeah.
So then if it's not combining those packets, then it's not going to have to recompute the checksums on TX. I'm not sure, because I think usually when you capture, it puts the NIC in promiscuous mode. I'm not sure how that affects GRO and whatnot. But if that changes that setting, then you might get a higher throughput and a higher CPU load.
Yeah, we have to look at that. But
anyway, it sounds like there's something weird going on in the checksum computation, and if we fix that, maybe that will. I mean, we should fix it, no matter what. But it sounds like that could be what's going on here.
For me, the question is, although, or my gut feeling is, does it really have something to do with a checksum calculation? But what I'm thinking is, do we have a problem with descriptor fetching? Reading the wrong bit in the descriptor for whatever reason.
Yeah, that's a problem.
Makes the checksum.
It sounds like the issue is not in the checksum computation itself, but the issue is somewhere between the reading of the descriptor, or somewhere between when the descriptor is written and when the checksum is computed. So there's several points at which that could be a problem, right? Either the descriptor is written wrong by the driver and that bit is set incorrectly.
Yeah.
That's one possibility, right? Maybe that gets corrupted somehow before it gets read, or it gets, something gets screwed up during the read, or once it gets read into the internal memory, maybe it gets screwed up there somehow. There's some
yeah.
other DMA operation that hits that same bit for some reason. Let's see. And then after there, then it gets handed off to the in this case, the transmit engine. So it's possible something happens along those lines. It's possible the transmit engine does something wrong with those bits. There's definitely a number of places along the line where something could potentially happen. Why it's only happening on the Intel devices, I don't know. It seems like if we had something weird going on with the DMA engine causing data corruption, we would be seeing lots more checksum issues, right?
Yeah.
It seems to be that the data itself is being sent properly. It's only this one random control bit.
Yeah, perhaps just to give some numbers here, where we over these 30 seconds, we are roughly transferring 13 million packets. And Uli, what was the number? I guess 17,000 or something have wrong checksums.
Yes, so in the range, yeah.
Yeah. Interesting.
So perhaps now another data point. We didn't repeat that test recently, but in the past we took 2 of our MQNIC based cards and bridged 1 port of each card together. And at least back then we didn't do any capturing, but we can just say that the bandwidth is almost as expected, meaning 9 point something gigabit per second for the TCP payload. So we have to repeat that test and perhaps do some capturing there too. But I would say that's a really strong indication that something is going on in the multiplexing, demultiplexing of the PCIe interface towards the MQNIC core and the 2 separate interfaces for our 2 separate ports.
So you're saying using 2 ports at the same, or 2 interfaces at the same time seems to be potentially causing a problem.
Yeah, that would be the conclusion. Yes, we have to repeat the test and also do the capturing, but we did it once and we saw almost perfect performance, almost not perfect, but almost way better. And that really points, for me, that points to a problem in the multiplexing of the in this case 2 MQNIC interfaces onto the PCI Express bus in quotes. And perhaps there in this multiplexing something gets mixed up regarding descriptor fetching. The question is, why is just descriptor fetching apparently mixed up, and why is it only the enable bit?
Yeah.
I mean, why isn't it the checksum start and checksum offset information, which is in the same D word?
Well, it's possible that those are basically set the same for every single packet.
Yeah, sure. Yeah.
It's possible, yeah. Although,
but on the other hand, if the software wants to disable it, the driver writes a yeah, right. And by the way, we also obviously we didn't check every single packet, but Uli, you tackled it with a little dissector for Wireshark to check the payload of these broken checksum packages, and iPerf always sends the same pattern, and I guess it looks good. So the corruption was just in the TX checksum field. No other field seems to be wrong. Not even the TCP options timestamp thing.
Right. Okay. Yeah.
So that's why I'm saying something is pointing to perhaps to the multiplexing of multiple interfaces onto PCI Express. And for some reason, destroying that single enabled bit, I don't know.
Well, from my point of view, it seems to be like I'm suspecting like an issue in the TX engine or between the TX engine and the checksum computation. That's it could be timing related, and that there could be a difference in timing between the Xilinx and the Intel devices, and the difference in timing if you're using both interfaces versus just one. So either some sort of back pressure signal that's connected wrong, something like that. Because I think that would kind of make sense and explain why it's affecting that particular bit. But for specifically what's going on, I'm not sure. So I'll do some poking around on my end and see if I come up with anything suspicious in terms of the code. But
I mean, one could also say it's definitely some kind of general timing issue, because as discussed before, when the CPU load gets higher, the effect is gone. So the stress on the interface, and that's why I think PCI Express first, the load, the stress on the PCI Express interface is lower then. And that's why I'm gut feeling. I mean, I'm more like a software person. Gut feeling is PCI Express multiplexing.
well, I mean, it's a thought. It doesn't make sense that it would be there and it would only affect this bit. We would be seeing a lot of other problems, I think, if there was a problem there.
Yeah. Also true. Yeah.
Yeah, it's like if we were seeing like 5 or 6 different issues, to be like, okay, but it's just this one bit. So it's like, okay, where is that only one bit going to be kind of by itself, where it can be influenced by some sort of an issue? And that's not PCI Express, because there's going to be a lot of different bits that get moved along that same path. So
okay.
Anyway, I'll take a deeper dive on the transmit engine and the connections between the transmit engine and the transmit checksum module, and see if there's anything obvious that pops up there.
Okay.
Because that's kind of where I think the problem might be. So we'll see. Hopefully I'll find a bug and we can get it fixed.
Yeah.
That would be good.
Yeah, and the question still is, why don't we see it on Xilinx devices versus Intel devices?
Yeah, don't have an explanation for that.
Then kind of it has to be something synthesis related, or
right. Well, I mean, it's either that or it's something timing related, something about the ordering things that are happening in, or the relative timing of certain DMA operations on the Intel is somehow triggering it, versus on the Xilinx it isn't.
Okay.
I mean, it's like that's the only thing that makes sense here, because if it was a problem kind of at the PCI Express level, and we were getting data corruption there that was affecting this bit, it would be affecting a lot of other stuff. So yeah, that's why I'm thinking it's going to be related to that, but I don't think there's necessarily a bug there.
Would that explain the behavior using 2 ports on the same card versus 1 port of 2 separate cards?
Well, I mean, obviously that's going to affect how much traffic there is going over PCI Express and through the DMA engine and whatnot, and that's going to change the relative timing of things, right? So change the load, changes timing, potentially changes what's going on at the higher levels, basically. So yeah, I'll take a closer look and see if anything pops out, but that definitely kind of narrows down what's going on here. Because yeah, I was thinking before, it's like if this was actually a problem in the checksum computation, you would expect something like maybe half of the packets, maybe, or something like that would
Yeah,
have the wrong checksums, or all of them, right? Not some very small number, right? If we're talking, a percent or something like that, or less, it's got to be some sort of sequencing issue, ordering issue, back pressure issue, something like that.
Mhm.
For that kind of number of errors or error rate, that makes sense. So yeah, okay, that's at least shedding some more light on what's going on here. So
Yeah.
I'll take a closer look at those modules and see if I see anything weird, and I'll certainly let you guys know.
Okay, sounds good.
But yeah, good job on your end for helping to sniff out exactly what the problem is. And getting some insight as to where it is, because previously I'm like, if I don't know where to look, can't make any progress on actually solving it.
Yeah.
All right.
Yeah. Okay. Yeah, I guess that's it. Uli, do we have another topic?
I think there was something we did want to talk about, but it's nothing too important. I think I don't get it. I don't recall it right now. So
all right. Well,
it pops up at some time.
Yeah, and you guys can always pipe up on Zulip or whatever if you have something important. All right.
Yeah. So, but one thing. So we just got a Stratix 10 MX card for reference. Okay. So that's good now.
So the Stratix 10 MX dev kit.
Yes.
The gigantic silver box thingamajigger.
Yes, right. With this, I don't know, 40mm fans mounted on it.
Yeah, that thing moves a lot of air.
Yes.
Very, very, very over-engineered card, I will say. With that huge metal box that they got on there, but yeah, it's a nice card. The other kind of fun thing about it is it's got two PCI Express slots, right? One male and one female, so you can potentially do some sort of a pass-through thing. I haven't done anything with that myself, but whenever I look at that card, it gets me thinking about, what can we do with that? Anyway, that's good. So you guys can run that. So we have another dev board in common then. So
exactly, yeah, that's very good, especially on the Intel side now.
Right.
Actually, yeah, that's one thing I wanted to mention. So we also did some have some progress on the transceiver ODI side.
Oh, okay, cool.
So we have an XFCP based design for our custom card that's now able to do iBird and iScans.
Well, Intel equivalent, but yeah.
Yeah, all right, exactly. So via these ODI registers. And what we will do, I guess, now that we have a Stratix 10 MX dev kit, we will port this to it, which definitely will take some time because we need to bring up our own cards first. But at some point, we will port this to the Stratix 10 dev kit, and then we can upstream it or discuss how to upstream it and so on, because that's the same thing you have, right?
Right, yeah.
So, and I guess it's already an example in XFCP, so we can just add this.
Right, yeah. Yeah, I mean, I'm thinking for XFCP, we may need to kind of pull some of the code from that example kind of up into the core, right? So
possibly, yes.
Yeah, it's been a while since I've looked at that, but yeah, it's like I think some of those tools might be better served in the core, so you can use it on any board. Because I think right now it's kind of board specific, but yeah, we can definitely revisit that. I mean, it would also be nice to be able to get the ODI running under Corundum as well.
Yeah, so that's the next step,
in terms of additional logic resources. Just mainly, I think, just bridging the transceiver control connections to, which is like an Avalon memory mapped interface, bridging that to the register space. So
yeah, so the interesting part
is
a
couple of other odds and ends, but yeah, it shouldn't be a big deal.
So the thing is that we actually implemented an Axi-Lite to Avalon memory map bridge to connect all these interfaces to XFCP. So that's what we do right now. Axi4Lite XFCP node, bridging this to Avalon memory map, doing some address conversion, and then going into these transceiver interfaces.
Oh,
So we can reuse this for Corundum as well, and then just rewrite the procedure in a C tool or something.
Right. Yeah. Okay. That'd
So I
be
guess
good.
Yeah, so that'll be now the experimental prototype, and once this is done, I guess we can just port this to Corundum as well. And at the same time, we started to work on using the Stratix 10 mailbox client IP to talk to the SDM.
Ah, right. Okay. Firmware
Because
updates?
that's right, exactly. Voltage measurement, temperature measurement, and firmware update.
Ah, okay, and also monitoring. Yeah.
So we haven't been playing around too much with it, but I just have a first design now ready with this one built in, and I'm hacking some Python together to interface with it via XFCP as well.
Okay, nice. And then
So
I guess the hope is that we can integrate that with Corundum, down the road at some point. I think the main thing that would be useful is the ability to write to the flash and update the
exactly.
Actually, speaking of that, I've been thinking it's probably going to be a good idea to think up a kind of a standardized firmware update format that can be used for everything. Because it's one thing to use bit files, but the bit file doesn't really have much in terms of metadata and whatnot, in terms of where to write stuff and things like that. I know for Xilinx device, it's usually pretty simple, right? You just strip off the header of the bit file, and then you write it to the appropriate, either the beginning of flash or to halfway up the flash or something like that. But the Intel devices, they seem to have a more complicated flash device format. And there might not be kind of as nice of a way to automatically figure that sort of thing out. So what we may want to do is have a some sort of more comprehensive format that can support more complex flash layouts, as might be required on Intel boards specifically. And it could be the case on other boards too, like maybe you have some sort of firmware that also sits in the flash for a soft core or something that also has to be updated separately from the actual bit file or something like that. So
Yeah.
kind of my thought at the moment is, don't reinvent the wheel. What I think we should do is make the firmware format like a basically a compressed archive of some sort, like a zip file that we can put bit files, binary files, whatever in there, along with some sort of a metadata file. And the metadata file would either be like an XML file or some other kind of text file that describes, firmware versions, build dates, that sort of thing. And then also what files need to be written where, and potentially can support things like, modifications, right? If we need to patch a couple of bytes here and there for a fallback boot bit stream that changes WB star, things like that, have kind of a standard format with a few operations that the firmware update tool knows about and then can do the right thing. And it might be worth kind of starting to think about this so that we can put something together that'll work for, both the Xilinx and the Intel devices.
Yeah.
If that makes sense.
Yeah.
And the other nice thing about
totally
using just
sense.
like text file and zip file is that you could use a make file and batch scripts to create it.
Yeah, I guess that makes sense. The easier and simpler it is, that's the more people can use it, I guess. So
right,
it's always a good idea. Definitely with respect to the Intel devices, they have a dedicated flash format. So they say don't use JIG files. That's tool version dependent. Don't use ZOF files. Please use RBD files that can be generated as well. So that's their advice.
RB what?
Let's see how this
RBF?
works. RBD.
RBD.
Mm-hmm.
Okay. I really like the way Xilinx does this stuff. It's very simple. Intel, they make things way more complicated than it needs to be. I've taken a look at both the SOF and the POF file formats to try and figure out what the heck is going on in there and how they're related and whatnot. And I
No
figured
chance.
out I figured out partially by looking at some C code from Bitware, the POF file format and how you can extract the RBF out of the POF basically. But I've never heard of an RBD, and I have no idea how you get from a SOF to a POF. Just looking at things in a hex header makes no sense.
So the worst thing is that depending on the device series you have, and it's the earlier before StratX 10 and StratX 10 onwards, I guess, they use different flows of generating binary files. So that's really strange when you're using these tools. It's really, as you said, it's pretty complicated and a lot of confusion around this. Yeah, I'm not sure. I think they were missing just one rewrite that Xilinx had with the transition from ISE to Vivado.
I mean, even with ISE, it's the exact same. The bit file is just the binary config data with a header attached. Vivado used the exact same format.
Yeah, but the way you're using the tools, right? It's much easier with Vivado, I guess. So before, in former times, you had the programmer and the other tool for generating the flash files and blah blah blah. So there were like these three tools to use, and now it's just Vivado, and it's pulled together, and you just change the view, and everything is okay. And for Intel, you need to use at least multiple tools, multiple windows, juggling around. If you configure things, then there is some XML files. You don't understand how the values get in there.
Right. Yeah. Well, okay. So the other thing about Intel, like I said, is that for whatever reason, the format, the data that goes into Flash is quite different, right? With Xilinx, you just write the bit file to address 0 and you're done. With Intel devices, for whatever reason, they have like some sort of a table at the start of the flash memory that has to be configured properly, and then that based on that table there's partitions that you got to load the bit files into, or not the bit file, the config files. But there's potentially a bunch of partitions. It's I don't really understand exactly how all those pieces fit together and whatnot.
But some pieces are easily explained. So there is this SDM that uses some of the partition data for configuration data and firmware data. So these are at least one.
I mean,
at least one partition, maybe
it makes
two.
sense once you dive into it, but it's just like Xilinx, just like one config form, one block of config data. You just write it to address 0 and you're done. That's it. For Intel, it's like, oh, you got like 5 different things that come from different sources that all have to be written to these specific offsets and yada yada yada. It's like, what are you doing? Where did all this come from? Yeah,
essentially,
I guess
think
it makes sense. You can explain it, but there's a lot more manual stuff involved. It's not like just write this one file to this one location and you're done.
Exactly.
Especially
but I think
because,
from a mental model, if you compare it with an MPSoC, it's more like the MPSoC boot model, right? Where you have this PMU and CSU and stuff to be brought out of reset, and they initialize and so on. And that's the same here. So there is processors involved that need to be configured first, and then the FPGA part is configured, and that's what's done here. And in all the other exciting stuff, there's nothing in there like this.
If you're trying to avoid the whole complicated SoC boot process, you can't avoid it on the Intel devices, basically, because they all boot like that.
Yes, that's right.
On the other hand, Xilinx, they have their boot bin file for the sync parts.
Right.
And that's kind of, well organized. You have one file, you write that at a certain location on the SD card or in QuadSpy or whatever, and that's it. So it's still the same simple thinking there.
Right. I guess in Quartus, by writing everything out separately, that makes it easier to update just 1 or 2 pieces instead of the whole shebang in one shot. So that's potentially an advantage, especially in secure applications where you only want to update, like one piece and not everything. So I don't know. I mean, I guess there are advantages to doing it that way. It's just a lot more complicated. Anyway, and I guess the other thing is that in the case of Corundum, we can't use the Intel tools directly to write to the flash, right? Because you don't necessarily have the JTAG connection. You got to go through PCIe. It's like initially you use the tools potentially to write to the flash, but once it's up and running, installed in the server, then we have to figure out what all the steps are to update everything appropriately. So that's one of the complicating factors. With the Xilinx devices, you just write the config files to the appropriate locations, which is just 1-bit file to one location, and you're done. With the Intel devices, you potentially need to do more than that. So, yeah. It's been a while since I've looked at the config documentation for the Intel devices, and I haven't looked at it in great detail for the Stratix 10 devices yet. So it's good that you guys are getting a head start on that. Oh, and then I guess the other thing too is just how you even access the flash, because not all Intel dev boards actually have the flash directly connected to the FPGA, which is really annoying. So I think there's going to be a lot of dev boards where you just cannot update the firmware over PCIe because the doofuses that designed the board didn't think about that use case.
Yeah, it might be the case that we need to update another device as well first.
If you even have the physical traces to do that.
That's right.
That's the problem. Yeah, because the Stratix 10 MX dev kit seems to be kind of the odd man out of most of the Intel dev boards by actually directly connecting the flash chip to the FPGA. Pretty much everything else, the flash chip is not directly connected to the FPGA. There's a Max 10 FPGA sitting on the board that sits in between the two. And that FPGA is also used as the USB JTAG in most cases. So you'd basically have to re-implement USB Blaster if you wanted to update that thing. And in a lot of cases, they don't provide any additional connections between the two, besides the Avalon streaming connection, which I think goes directly to the SDM. So you can't, I don't think, do anything with those pins besides just receive the config data that gets dumped on you by the Max 10 part. So like the Stratix 10 DX dev kit is like that. I don't think it's possible to update the flash without using USB JTAG on that board. It's just due to the design of the board. This is something I've griped about before. I don't know why Intel designs their dev boards like that. It's really annoying.
I'm not sure. Never looked at the DX dev kit yet. So maybe, yeah, I don't know. Maybe there is something how to do this. Not sure.
Yeah. The 520N MX board from Bitware is also similar in that there's a Max 10 part that sits in between, but they have some cooked up interface between the two that will enable the FPGA to access the flash via the Max 10 FPGA. I haven't looked in great detail exactly what that interface looks like, but it's not something standard. They cooked up something strange just for their own board. So yeah, it'd be one thing if they had a standard technique, like you hook things up this way, and then there's a path, and it's pretty easy to support. But no, every board's got to do it their own way, and they're all different. So versus all the Xilinx ones, they just hook it up directly, and you do the same thing on pretty much every board, and it just works. So anyway, enough ranting about Intel's weird board design methods. Let's see. What else is there to discuss? Is that everything that you guys wanted to discuss in terms of what you guys are working on? I know you said there was one other thing, but I guess
I think that's it for me, from my side at least.
Okay.
Yo, I'm good too. Nothing more.
All right. Sounds good. I guess we'll go ahead and adjourn the meeting for today, and we'll see all you guys in 2 weeks, which will be November. Let's see. Today's the 24th. we go to November 7th, I guess. Well, all right. Sounds good. See you guys in 2 weeks then.
See ya. Thank you, everybody.
All right. Thanks everybody for tuning in.
Thanks a lot. Bye.
See ya.